right. Hello, everybody. My name is Brian Behlendorf, like you heard. I'm a computer scientist at Lawrence Livermore National Laboratory, and I founded the ZFS and Linux project. And I wanted to talk to you guys about the use case we're using for ZFS and how it's become instrumental to our machines there. But first, I wanted to mention that I really think the BCC stuff is really cool, and I'm going to look into that from the previous talk, because that kind of analysis is exactly what we need to drill down on problems. So I'm pretty excited about that. This talk, however, is going to go in a different direction, right, for the biggest scale machines out there, which is something we do at Livermore. So let me talk about that for a minute. So Lawrence Livermore National Laboratory, we're located in the Bay Area here. We're actually only about 40 miles east of here, so local. Livermore is one of 17 Department of Energy facilities scattered around the country. Department of Energy actually runs a lot of research facilities. They're primarily research and development facilities for the federal government to do long-term strategic and technical research. And Livermore is one of these. They're broadly speaking broken into two parts. There's the Office of Science Laboratories that do a lot of fundamental research, and then the NNSA laboratories that do a lot of national security related research. So I work at Livermore, which is one of the NNSA laboratories. Los Alamos is probably another one you're familiar with, right? That's the home of the Manhattan Project in World War II. The atom bomb came out of there. And Sandia is the other big laboratory. There's a lot of overlap between the research done from a lot of these facilities, but they're all research and development. So this is Livermore. It's about a square mile campus, like I say, just located east of here. It was founded in 1952, actually, by the University of California. Interestingly enough, Livermore used to be a World War II naval air base. So what was sited here originally was a radiation laboratory that was managed by the University of California, and that grew effectively into Lawrence Livermore National Laboratory. So the laboratory was originally set up in this capacity in 1952 as kind of a counterweight to Los Alamos. Like I say, Manhattan Project started at Los Alamos, and they did a lot of the nuclear weapons design work in the country at the time. In fact, they did all the nuclear weapons design work. And then in 1952, people thought it was a good idea that maybe we should have two laboratories working on this. So one of Livermore's primary missions is as a nuclear weapons design lab. They have other missions, but that's one of them. And like I say, they're set up as a counterweight to Los Alamos to, act as a sounding board to review designs and whatnot. So, as I mentioned, NNSA is that component of Livermore, the National Nuclear Security Administration. Basically, one of the main missions at the laboratory is a program called stockpiled stewardship. So stockpiled stewardship is basically our laboratory certifying that the nuclear weapons in the US are safe, reliable, and effective, that they're going to work. And this is a pretty hard problem, it turns out, because we used to do this in the US by actually testing the weapons, right? And this was, every year we have to report to Congress that the weapons will work. And this used to be done by testing them. That can't be done anymore, right? In 1996, there was a nuclear test ban treaty that was signed by the US, as a little bit of background, which basically said no more above ground nuclear testing. So we don't do that anymore. And the way we still certify the stockpile is with simulations. In fact, HPC simulations for high performance computing simulations is one way we do that. So that's part of our mission. But I don't want to let you think that that's not our only business. We actually are a research and development laboratory. So one of the other big projects operating at Livermore right now is the National Ignition Facility. I don't know, has anybody here heard of the National Ignition Facility? Right, so this is probably one of the coolest projects at Livermore right now. It's basically a giant laser, right? So the National Ignition Facility is a fusion research experiment, and it's designed to simulate the temperatures and pressures that are required for nuclear fusion. So you're talking about hundreds of millions of degrees, billions of atmospheres of pressure for a fraction of a second to get fusion. And this might look like a picture of the warp core from the fairly recent Star Trek movie, but in fact, this is a picture of NIF, right? They used it as a background. So that actually is the target chamber for NIF that they're standing in front of, and that's a cool little bit of science that's going on at the laboratory. In fact, it's a big bit of science going on at the laboratory right now. You think so?
Yeah, that's very Empire color scheme.
Yeah, I like it. It doesn't look that Star Trek-y, huh? Well, anyway. So we do a lot of other research at the laboratory, but those are two of our primary missions at the moment. But we actually have a long history of scientific computing going back to support those kinds of technical missions all the way back to the 1960s, actually a little bit before that. So like I said, we were founded in 1952, and then we brought in the first HPC machine to the laboratory in 1953. So pretty much immediately after the doors were open, we started deploying hardware there, and that was a UNIVAC 1. So going way, way, way back, they have a nice computer history museum associated with the laboratories where you can see some of these things. And the UNIVAC 1 is a beast of a machine, right? It's, 7 feet by 14 feet, and the whole thing has 5,000 vacuum tubes in it, something on that order, right? And 1,000 words of memory. That was the UNIVAC 1. But anyway, historically, we've deployed the latest, greatest supercomputers at the laboratory in support of these scientific computing missions over the years, and to do a lot of scientific modeling for, various programs. So supercomputers these days are ranked, on a list called the Top 500 list. It is exactly what you think it is. It's a list of the 500 fastest supercomputers in the world at any given time. The list is put out twice a year. Once at supercomputing and once at international supercomputing, so every 6 months. And the systems are ranked using a benchmark called LINPACK, which is kind of interesting and kind of an accident of history, actually. Right? It's not that this benchmark was designed for this purpose. It's just the one that everybody happened to use, and it happens to be a pretty good measure of the computational performance of a system. So you could imagine that one way to measure a computer system, right, would be to multiply out all the processors, right? I've got 1 million processors and they're all this fast, and that's the theoretical peak performance. Well, LINPACK actually gives you a measurement of the actual delivered performance to an application, right? So it does this by solving a series of linear equations spread over the memory in the system, right? So it measures things like the effective memory bandwidth of the system, like how fast the interconnect is, how fast it can pass messages around, what the CPU speeds are. All those things come in to give you a measure of the computational performance of the system. Again, it's an arbitrary benchmark, but it's the one people have settled on for 20 years now. At the moment, Livermore has had 2 systems in the last 10 years on the list. We've had more than that going back, but like I say, Blue Gene and Sequoia here had the #1 spot in the last 10 years, which is pretty cool. I got to work on both of these systems, and they're pretty neat. DOE, like I say, has a complex of laboratories, and at the moment, there's actually quite a few machines spread out over that complex that are in the top 10. Oak Ridge has a machine called Titan. It's about 17 petaflops. There's the Sequoia machine, which I just mentioned at Livermore, and Lannel and Sandia have a machine they just deployed called Trinity. So interestingly enough, this list used to be dominated by machines at the Department of Energy, HPC machines, but in recent years, that's not been the case so much. Right? Some of the biggest machines we're seeing now are actually coming out of China, with just monster processor counts and performance numbers on them. So we got a little competition now, which is cool. So at Livermore, our computing environment for these machines runs Linux. Right? This hasn't always been the case, but about 2000 or so, we made a pivot to Linux, basically for reasons you might imagine, right? Linux kind of took over that space. We wanted to be running commodity hardware as much as possible because while supercomputers are big and expensive, and they used to be proprietary, there's only a limited volume of them, right? I mean, we'd really love to be running commodity chips. Well, whatever they're making 1 million of or 10 million of or 100 million of, right? We get much better prices on that. So there was kind of a strategic shift in the last 10 years or 15 years to Linux computers for that reason. We build our systems on top of Red Hat Enterprise Linux because, once again, it's an enterprise distribution. We've looked at some. Ubuntu is definitely an option for this, but we happened to settle on Red Hat a while back. And to this, for our distribution, we add some HPC-specific functionality that you don't find in most Linux distributions, right? So that means things like low latency interconnect. InfiniBand is the current interconnect of choice these days, mainly because it's got such low message passing times, and great bandwidth. It's actually got a lot of things going for it. But over the years, we've gone through a lot of proprietary interconnects, right? At the moment, InfiniBand is the one we're using. Our parallel file system of choice is Lustre, which I'll touch on in a second. And then you need a resource manager in the stack to basically effectively schedule jobs over these thousands or tens of thousands of nodes, right, and cores. And Slurm is a resource manager that was originally developed at Livermore, and we're now using. There's actually efforts underway to develop a new next generation scheduler. We'll see how that goes, but that's being worked on because there's, new problems that need to be solved in this area. So we're looking at that. And then we add some cluster administration tools just to manage the whole thing. But one of the key ideas around Linux computers also is doing this with open source solutions, right? Given the options, we really want to use open source. Open source like ZFS or Lustre or Linux, right? We have a substantial investment in these machines, and we have the staff to maintain and work on them, and we want to be able to work on the guts. So we're a big fan of open source solutions and engaging with the communities around them as much as possible. So this talk is about the storage side of things. So I thought I'd address that a little bit now that you've got a little background on, kind of what we do with the machines and, what they're there for, what they're simulating, what our mission is. So scientific simulations like the ones we're talking about, there's lots of different simulations we do on the systems. Can easily generate petabytes of data, right? They just generate enormous data sets. They need to be stored. And there's quite a lot of variety in these data sets, actually. We have data sets that range from millions of small files to, really huge multi-terabyte or even multi-petabyte files, right? We give the users quite a lot of latitude in what they write out in their data sets. So we really need a general file system that can handle that, right? Unlike a lot of places, I would say, well, maybe not a lot of places, but I'll go out on a limb and say that I think data integrity is probably more important to us than a lot of sites. You can imagine that if you're doing a big scientific simulation and you're reading a data set back off disk or something to continue calculating, and you read in some wrong values, right? And you continue simulating with that. And suddenly, voila, you've discovered new physics, right? Not so good, right? We don't like that, right? It's a whole different scale of problems rather than a couple pixels are wrong in my Facebook image or whatever, right? It's much more important. So data integrity, right up our alley, a big thing we care about. We go through a lot of effort for that. On the back ends, our file systems also really require high I/O throughput for checkpoints. This might not be obvious initially, but for systems that are the scale of Sequoia or some of the biggest systems, right, you can be talking about having a petabyte of memory on the system, right? And that petabyte of memory needs to be written out at periodic intervals because while the systems are reliable for the most part, they're huge and parts do fail in them. So you might lose a node, right? And you don't want to lose the whole calculation, right? You don't want to lose the whole simulation. So you periodically want to be writing out these timestamps or checkpoints so you can restart in the case of a failure. Now, you want that to be fast because the scientists at the end of the day, they don't care about writing out data. They want to do the computation. They want to get the answer, right? So they need to strike a balance between how much of their time they're spending calculating and how much of this time they're spending doing I/O. So we want to make sure we deliver good bandwidth on the back end so that they can minimize those I/O times as much as possible. And you can imagine writing out a petabyte of data takes a little bit of time, even on a fast file system. And then we can't just optimize for I/O throughput, as nice as that would be, all right? At the end of the day, they're going to want to visualize this data. So the requirement there is that they actually have decent interactive performance also on the file system. We use tools like Visit, which are really good at providing visual simulations, like you can see up there, of the data in the file system or the particular simulation. And that requires decent interactive performance and not something like a batch job. Most of the jobs run on the systems are batch jobs, so they don't feel the I/O time for checkpoints and whatnot. So as I mentioned, Lustre is our tool of choice to handle these workloads. Lustre is a scalable, distributed parallel file system. So you can think of Lustre as a POSIX file system that's mounted on all the nodes in the cluster and provides coherence across the cluster, which is a surprisingly hard problem. But Lustre is hardware agnostic. Again, we like this because we like to deploy whatever the current new hardware is out there or the best solution for it. We have lots of vendors that bid solutions for hardware for us. This stuff gets competitively bid, so having them be able to bid whatever they think the right solution is really, really flexible and powerful for us. Again, we like open source software, right? Lustre is all open source. It was originally put under the GPL v2, and this has the usual advantages of open source. No one company controls Lustre, which again is good for us. There aren't that many parallel file systems out there, but we really want to be able to work on the guts and develop this out in the open with other HPC sites. And this helps protect our investment, our substantial investment in storage and whatnot, right? We were sure that this isn't going to go away on us one day. Plus, there's a large, active, motivated development community around Lustre. It's really gotten a fair bit of traction. It is used probably predominantly on most HPC systems these days, right? 7 of 10 top supercomputers for a lot of years have used Lustre. And like I said, it's a POSIX compliant file system. And well, this might sound like a small thing these days, right? Because there's lots of people moving away from this model, right? In the cloud in particular, like providing POSIX semantics for a distributed system really just isn't done because it's a hard problem. But our use case is a little bit special here. We care a lot about POSIX compliance because, as I mentioned, we're an old laboratory that's been doing simulations for a long time. And we have a lot of old codes. And we'd really like to keep running those codes, right? There's scientists and code teams that have been working for decades in cases on these codes, and they're really not so interested in rewriting the code or re-implementing it every few years because we found out a great new model for how to do this, right? So POSIX compliance is a big deal for us. We'd like to shed it at some point, so I don't want to close the door on that. This is certainly a thing we're looking at, but at the moment we have so many applications that depend on it that it's really important for us. So we get all these things out of Lustre, which is great. Lustre is a community, has a lot of community organizations, or at least a lot of community involvement, I should say. There are 2 organizations that do Lustre support and help development and organize things for the community. OpenSFS was set up in 2010, kind of as a place for vendors and the community to get together, much like OpenZFS is today. Right? Everybody gets together, we talk about technical issues, we discuss the systems we're building, all those things get addressed. EOFS is the European counterpart to this, right? But the same basic idea. It's kind of I don't want to say a smaller community necessarily, but a very diverse community of people who run this supercomputers like this. So architecturally speaking, there's a lot of data on this slide. We don't really need to talk about most of it. But architecturally speaking, the thing to take away from Lustre is that fundamentally it's split into metadata and data. And this is kind of the important bit. So way back when Lustre was created, right, this was a fundamental decision that was made, that we wanted to separate all of the block data from the metadata, at least as much as possible, because it allows us to do things like get good write throughput on the system. Right? If we can actually engage as many clients as possible, writing to the servers as possible, without making them get involved in timestamp updates and things like that, we can get much better throughput for the system, which is really, really important to us. But at the same time, we do care about it being a POSIXly consistent file system, right? So we have to do that kind of thing. So a balance was struck to keep them separate, and a complicated locking system was developed to get us POSIX coherence out of this. The result is a really high-performing file system for bulk data and good metadata performance out of it too. I should say that the metadata performance is being improved, and one of the recent features to Lustre is distributed metadata. In the picture here, you've just got one MDS, so that's the metadata server. But in newer versions of Lustre, you can have more of these, right? And you can scale out the metadata, which is a big deal. Like I say, we care about not just throughput, but also interactive workloads. So this worked all really well for us for a long time, ever since we deployed Lustre back in 2003, I think. We had a machine come in called MCR, which was one of the first deployments of Lustre, maybe the first deployment of Lustre at scale. And that served us really well up until about 2013. And then we started looking at Lustre and saying, maybe it's not going to scale where we needed to scale. This is the Sequoia system, a high-level architectural view. And it's a big system, right? This came up on the books as something we were going to field and deploy, and we were looking at how are we going to develop or deploy a 54 petabyte file system, a single file system, not 54 petabytes of small file systems, right? One 54 petabyte file system with almost a terabyte a second of throughput. And while Lustre scales really, really well, it probably wasn't going to scale well enough for this. So we needed to look at like why that would be. So the reason that we were worried in particular is that even though Lustre handles lots and lots of servers pretty well, we're talking about numbers in the hundreds or maybe low thousands, right? You can deploy 1,000 storage targets, right? But beyond that, you start running into some limitations, right? The clients have to individually track each of these storage targets and manage some small amount of state for it. So the more storage targets you build up, the more work you're putting on the clients that's using up resources that might be used for compute instead, managing the clients. So what we really wanted to do was build bigger storage targets with Lustre. And we couldn't do that, it turns out, for really, really good historical and technical reasons. As I think everybody here is probably well aware, writing a file system is hard, right? In particular, writing a file system from scratch is hard. So Lustre focused on the areas where it was good initially, which was handling distributed workloads and parallelism and that kind of thing, and then built on existing technology for like actually writing the blocks to disk and actually reading them out, which wasn't the key problem they were trying to solve initially, right? So we built on the legacy ext file system for Linux. That worked great. Initially, we extended it and added features that later went into ext4 on Linux. Things like the multi-block allocator came out of Lustre. And we exposed some interfaces to get transactional object semantics out of ext, which was great. And this worked for a really, really long time. But the problem is we also inherited the limits of ext, right? And one of those limits is maximum file system size. It used to be originally like around 2 terabytes. That got pushed up to 8 terabytes. But fundamentally, it still isn't very, very big, particularly when you're talking about deploying a 50-odd petabyte file system, right? You're talking about 7,000, 8,000 servers, something like that. Too many for the clients to imagine. And from our point of view, this was the first machine coming in of this size, but they were only going to get bigger, right? It's not like this was the end of the road. The next one's going to be twice as big, right? So ZFS to the rescue. We'll finally get to the ZFS bit. Now that I've set the background up here. ZFS just is the perfect fit for Lustre, is the bottom line, right? This is exactly the thing we needed to solve this problem on our storage backends, right? It has all the things we need, right? It's scalable. Like I just said, that's a big deal for us because we always want to build them bigger. It's manageable, another big deal for us because, you know, we're going to have thousands of these things. We want them to be as easy to manage as possible. Performance actually works really well for us with ZFS because it's a copy on write file system, which isn't a thing we had before. Like I said, a lot of our workload is writing out checkpoints to disk. So it's a lot of writing, and it's a lot of writing from a lot of random processes, doing random writes. And the fact that ZFS is copy on write lets us serialize that all to disk, which is great for performance, right? Whereas before, with something like ext, we'd be writing blocks all over the place, just based on where the allocator wanted to put them. With ZFS, we can stream them. That's great. We have the advanced features in ZFS, and like I said, data integrity was another big one for us. So this was clearly the best choice when we were looking around for how to deploy Sequoia of a file system to use, right? It addressed a lot of our issues. And, oh, by the way, the ZFS source code had been recently released in 2005, right? So we were looking at this initially in, I want to say 2008, 2009, something of that time frame, looking to develop something as a better backend for Lustre. And at this point, you know, ZFS had been proven on real production systems. This was all great stuff, right? This is exactly what we needed. It kind of ticked all the boxes for what we wanted for a back-end file system for Lustre. But like all things, there were a couple problems, right? Problem number one, the Lustre server storage layering had to be redesigned a little bit. So while the original layering did consider having multiple backends instead of just ext for Lustre, the reality of the situation is that by only having one for a long period of time, the layering got broken here, and it got broken there, and things ended up in the wrong layers where they shouldn't have been, right? And there was going to need to be a lot of work to relayer this so we could support different backend types. So this is work that was actually tackled by the Lustre core developers, and it took a lot of releases to refactor this because it turned out that a lot of these assumptions went pretty deep in the stack. Right? But eventually, we refactored the stack for Lustre. The core Lustre developers did this work over a bunch of different companies, actually. Originally, this work started while Lustre was a project primarily run out of Sun, later acquired by Oracle and moved to another company called Wham Cloud. But this work continued over all of those various companies. Problem number 2, we didn't have ZFS on Linux. And that was kind of sad because, Lustre's a Linux file system, and we wanted to use ZFS because we saw how cool it was. But there's good news, right? We actually didn't need all of ZFS for Lustre. This is maybe something that's not so clear from the higher layers, but Lustre actually ties in to the DMU layer in ZFS. It's the first-class consumer of the DMU. It doesn't layer on top of the POSIX file system. It doesn't layer on a volume. The interfaces provided by the DMU are pretty much exactly what Lustre needs. So we tied in there. And this is work that was done at Livermore, actually, to bring ZFS onto Linux. And as you all know, we didn't stop there, right? We saw how cool this was, and we wanted the rest of it. So we implemented the POSIX layer 2 and the volume manager. So the Lustre ZFS implementation. Technically speaking, the on-disk format for Lustre is compatible with the POSIX layer. We did this for a couple of reasons. We wanted to be able to debug the file system pretty easily, and it was convenient to be able to mount the same data set that Lustre is using to store its objects as a file system and to rummage around and look for stuff, right? You could use all the normal system utilities on it, hex editors, DD, whatever you want. You could easily inspect the file system. We got to leverage all the features of ZFS from the DMU down, basically. So it turns out things like compression were actually a really big win for us early on. This surprised us initially because a lot of the HPC workloads depend on libraries, and libraries have compression algorithms built into them. But they didn't work as well as you might have expected, actually. We got huge improvements in compression on the file systems at no cost to performance just by turning on compression. So that was a cool win. Like I said, we're layered on top of the DMU, and this work exposed a lot of assumptions we had on the client side in Lustre. Things like the maximum object size happened to be hard-coded, 2 terabytes. That was an EXT limit. The block size, we assumed it was a page size over the years, right? Because it always had been with EXT. Turns out it's not always a page size with ZFS, right? It can be much, much bigger. So at this point, we've deployed pretty much all ZFS and Lustre at Livermore in support of our HPC workloads. We've got about 10 file systems deployed with maybe 100 petabytes in production. There are new file systems being deployed at the moment, actually. But we're pretty much all in on this ZFS Lustre thing, and it's been working out really, really well for us. But we're not the only one. While we were the only ones to do this initially, it turns out that a lot of the other HPC sites have decided that this is really a good idea too, and they should be doing the same thing. It took a little while because it takes a long time to design, build, and deploy an HPC system. But Los Alamos now has 2 14-petabyte file systems of the same design. San Diego Supercomputing Center, 2 7-petabyte file systems, and there's vendors out there now selling these systems, right, to anybody who wants to buy them, pretty much. And there's lots of smaller deployments at universities, research labs, which are cool, but not the big file systems. And mainly where you need ZFS is for the big file systems, right? So Aurora. So we're not done. While Sequoia was, like I say, the first step along this route, Aurora is a big system designed for the 2018 timeframe, right? It is going to be 3 or 4 times bigger than Sequoia, depending on how you measure it, right? It's got 150 petabytes in the file system. It's going to be a gigantic machine, right? And it turns out that because of the work that was done with ZFS, Aurora is going to be built on Lustre and ZFS. It's one of the reasons they can build this machine as a file system. So this is driving quite a lot of the current development, at least on the HPC side for ZFS, right? There's work going on to improve Lustre's integration with ZFS in some areas here. And then there's features that are being added to the core ZFS code to improve HPC workloads. Things that might not seem so important on smaller systems are really important for big systems. Things like inode quota accounting, right? When you've got 1 billion or 10 billion files in your file system, being able to get those numbers and be able to quickly get that information is really important. Like, which user out there has 1 billion files? I want to know that. And then there's all these other features we're working on too, which we can talk about later, and I'm sure we'll talk about at the lightning round tomorrow, or lightning talks tomorrow. But the bottom line here is I would say that OpenZFS has kind of become a really important building block for the largest HPC systems out there. It's what the biggest systems are getting built on. And that's really exciting to see. And that's thanks to all the hard work done by you guys, which we appreciate immensely. And it's helping us get our mission done at the laboratory. So I have a short video, if you're interested, in about a minute, about sometimes this stuff is kind of abstract. So let me show you a concrete example of what Sequoia looks like, or particularly Grove. This is the storage file system we built for Sequoia. We happen to, each one of these clusters gets a name, right? And the file system gets a name. And this is a time-lapse buildup of the Grove file system. So this is the 50-odd petabyte file system getting built. It's just so much activity. But I want to say about 30,000, something on that order.
What size are those drives typically?
Sequoia's pretty old, so I think they're about 2 terabytes only, something like that.
Have you ever seen disk failures?
I've 1 or 2, yeah, so it turns out they happen. I've seen some spectacular disk failures. This is my favorite part, actually, loading the drives.
Brian, do you guys publish any information on backplanes, test information, by firmware, by maker?
We don't actually publish any of that stuff. We'd like to, but it's actually a lot of work to gather that data and number crunch that data. So no, we don't publish any of that. We do track a lot of it internally for drive failures, but it's not available.
How much additional capacity do you give?
At the moment, we're seeing about, I think, about a 1.5x compression ratio on the file systems. So really, that 54 petabyte file system is more like a 75 or 80 petabyte file system, right, with real data stored in it. Yeah.
Because the storage is separate from the computing layer, what is the disconnect between the storage system and the
Good question. We've used a bunch of things over the years, ranging from 10 gig and 40 gig to InfiniBand. Right? Most of our stuff at the moment is InfiniBand attached because we get really good bandwidth out of it. So it's not uncommon for like one of those storage nodes to have the previous generation QDR InfiniBand links coming out of it. And there are, well, Grove had 768 of those nodes, right?
What does this look like from a single count layout perspective?
So the nodes on, I should go back. Yeah, I'm sorry. The question was what the layout of the drives was like on the systems. So individual systems for the Sequoia system are attached to NetApp JBODs, actually. So they aren't, and those NetApps are exposing volumes that we're running ZFS on top of. At the moment, NetApp's taking care of the RAID for those on the Sequoia systems. But the new systems we're bringing in, actually, are that next step, right, where we're going to a full JBOD system with ZFS, and it's going to handle the RAID steps. So we're getting there, but.
The drive failure data from CFS, but CFS has built in functionality for offloading those data. We should do it. One hard work on the hard.
So the question was, if it was easy to publish the drive data, would we? I think in general, we'd like to be open. So if it was easier, we'd certainly consider it. I don't know that our rules permit us to do that in a lot of cases. Certainly not for some systems, which are classified. But for other systems which are not, yes, maybe. It's something we'd at least look at.
What's your current and near-term use of Flash?
Flash. So systems like this, we're actually looking at a solution for I'm sorry, the question was, how do we use Flash? And the answer is, at the moment, we don't. right? So we don't use flash at the moment in any of the Sequoia systems, but we're looking at it for new HPC systems in a technology called a burst buffer. The idea is to deploy a lot of flash, basically, for the applications to checkpoint to, and they can burst to that really, really fast, go back to computing, and then we trickle it off slowly to storage. So we're looking at for technologies to do that. Yeah, so we've actually got a lot of work going on right now with Intel, actually, to get that done and to get fault management fully integrated on Linux and working. So there are pull requests outstanding and development work being done to make that work smoothly, because that is a big concern, and that's absolutely one of the reasons we didn't do full JBOD systems initially, is it's a lot of work to get that right. So, yeah. Yeah. Yes. I should have mentioned the name for that. So that's up on GitHub now. It's called the Flux project, or Flux framework, I suppose. You can find it on GitHub. It is certainly a work in progress that's being developed. It's designed for scalability for our largest systems, and the hope is to replace Slurm with it, but it's still something that's being developed. Check out the project. Ask questions. They're love to get some more attention on it. Mm-hmm. So I should have mentioned, Aurora is a system that's not being deployed at Livermore. It's spread across. It's actually going to be sited at Argonne. So just outside Chicago will be the Aurora system. DOE likes to spread its supercomputers around pretty much. This $200 million procurement is going to site there. I don't know offhand what their design is for the storage, but I know there are people here who can probably answer that question. The question was how many drives per OST for our largest file system. So the ones we're looking at deploying now are about 60 drives per OST. Yeah, so the intention is to deploy these as 5 8+2 or 6 8+2 RAID Z groups. We could go bigger, but 60 drives is about reasonable for us on a server. It's one enclosure's worth of drives. The nodes actually see quite a bit more than that. They also see all the drives from its failover partner, because we do failover on these systems, and often they'll see paths for multipath devices. We'll have multipaths to every one of these devices. So it's 60 times the other drives times 2, so you might see 240 different devices on the system. And Linux holds up under that, but it does strain a little bit when you've got that many devices attached to it. Certainly Linux has gotten much better about that, I should add, in recent years. It used to be that it would just fall over and die, but no, not anymore.
Is there I don't know how related this is or isn't to HPC stuff, but is there a roadmap for when we can start to see some of the new features from Delphix, ZFS, and ZFS on Linux, like defrag and VDEV removal and resumable send receive?
I don't know that there's a public roadmap for when those features will ship or anything like that, but all the development for those features is being done out in the open. Well, at least a lot of those features are being done out in the open in pull requests. And if you want to join the conversation or, help with getting that stuff done, that's a possibility.
Where would I go to join that conversation?
GitHub is probably the place to go. So either the Open ZFS project on GitHub, things will be posted there, or for features that are being developed first on Linux, ZFS on Linux. Just look at the open pull requests or the issues, search for what you're interested in. You'll probably find a ticket, and it'll point you in the right direction. We're certainly doing a lot more development in that area, right, to bring some of those new features. That's all I got. Thank you very much.